This is video 81 in our series on tensor calculus. In this and several videos to follow, we're going to re-examine surface curvature from a totally different perspective. What we will ultimately discover is that rather than using the curvature tensor, we can derive Gaussian curvature directly from the intrinsic properties of the surface itself. In the last few videos, we've developed the concept of surface curvature. In doing so, we relied almost exclusively on the curvature tensor. When we take this approach, we're analyzing curvature from what we call the extrinsic perspective. The word extrinsic simply means originating from the outside. So what we've been doing all this time is looking at the picture from the outside in. Let's illustrate using the spherical surface here. You'll recall that we made heavy use of the ambient space. For example, we defined a tangent plane like this as the plane that touches the surface in exactly one point here at our point P. We also defined a normal, which is the line that's perpendicular to this plane. And then we also defined the tangent space using a combination of our basis vectors here and the normal vector right here. Now, all of these objects are external to the surface, so we classify them as extrinsic objects. And the curvature tensor itself is defined in terms of these objects, so we have to classify the curvature tensor also as an extrinsic object. Now, consequently, what we call the curvature tensor is more properly identified as the extrinsic curvature tensor. To derive it, we have to know how the surface is embedded in the ambient space, and this comes from seeing the relationship from the extrinsic perspective. Think of it as the bird's eye view. We're analyzing everything from the outside in. In video 78, I pointed out that the principal curvatures and the mean curvature depend on the orientation of the normal, while the Gaussian curvature does not. Well, Gauss picked up on this idea and began to question whether it could be derived without reference to any extrinsic object. In other words, he suspected, correctly as it turns out, that Gaussian curvature is an intrinsic property of the surface. The word intrinsic means from the inside or pertaining to the internal nature of something. So what we want to do now is to analyze surface curvature from the intrinsic perspective. If the extrinsic perspective is the bird's eye view, then the intrinsic perspective is the bug's eye view. All we're allowed to do is to make distance, area, and angular measurements on the surface itself. No extrinsic information of any kind is allowed. The next several videos are going to be devoted to a detailed analysis based on this perspective. But for the remainder of this video, I want to illustrate at the qualitative level the kind of effects that can be observed using this approach. So to proceed, let's imagine a race of two-dimensional flatland creatures stuck down here on the surface. Now, they can move around all they want to, and they can take measurements on the surface. They can measure distances and angles and areas, that sort of thing. But they have no concept whatsoever of a third dimension, and thus they're oblivious to the ambient space or any of the objects that are derived from it. They're unaware that they live on a curved surface. Well, of course, that fact is obvious to us because we have the benefit of the extrinsic viewpoint. Well, let's see what our flatland creatures might be able to figure out using only the limited resources that are available to them. We'll start with our surface here, and we'll put a couple of flatland creatures on it. We'll put one here, we'll call him Bert, and another one here, we'll call him Ernie. Okay, of course, Bert and Ernie can measure distances on the surface, and they find out that they can put a rope or a tape measure between the two of them. So we'll just connect them with this line, and we'll measure the distance of that line segment, 1.4. So now Ernie can stretch out the rope and go in a circle around Bert over here, and he'll subscribe a circle on our surface. And both these guys are aware of plane geometry, so they know how to calculate the circumference of a circle and the area of a circle. So let's look at these numbers. They know that the circumference of a circle is 2 pi r. So if we multiply this value times 2 pi, we get 8.77. And if they measure the actual distance, that's what they're going to get right here. They also know how to measure the area. The area is pi r squared. Square this number, multiply by pi, you get 6.12. Measure the actual value, and that's what you'll get. So nothing remarkable here. This just tells us what we already know about how to calculate the circumference and area of a circle. Well, now though, let's move out a little bit. I'm going to zoom out. I'm not going to change the circle right now. I'm just changing the viewing perception. We're zooming out, looking from the picture from further away. And then when I get here, I'm going to enlarge the circle. Now notice what happens when I enlarge the circle. Look at the numbers over here. They're no longer equal. The actual circumference, this being the actual measured distance around the circle, is no longer equal to 2 pi r. The calculated value is greater than the actual circumference, and it's off by about 0.25%. Likewise, the actual area is no longer equal to the calculated value. The calculated value is larger than the actual area and is off by 0.38%. Well, if you're Bert and Ernie, you're confused here because you just knew these were the right formulas, so how can this be wrong? Well, let's continue to zoom out of the picture, and we'll keep going until we can see what you and I already know, and that is that Bert and Ernie don't live on a plane, they live on a spherical surface. We know it's curved. And as the larger the circle gets, the worse this error becomes. Well, you and I, from the extrinsic perspective, know exactly what's going on here. We know that these lines are not on a plane, they're on a spherical surface. So if we look at it this way, the value of r that Bert and Ernie are measuring is this distance along this curved line. Well, that's longer than the actual radius of the circle itself. The radius of the circle goes from here to the outside, and that straight line is obviously shorter than this. So when we calculate this formula, we're using the value of r, which is longer than the actual radius of the circle. Now, you and I know that because we can see this picture. But Bert and Ernie don't know that. All they've been able to do is to measure the distances and areas of the figures on the surface. Well, the fact that the calculated value comes out to be larger than the measured value, both in the circumference and the area, is a tip-off to these guys that they don't live on a flat surface. If they lived on a flat surface, these would be exactly equal. Let me point out, too, that if they lived, this surface is a positive curvature, but if they lived on a surface that had a negative curvature, such as a saddle shape, then we'd find that these calculated values would be less than the actual values. So the only time the actual measured values are equal to these formulas is when we are dealing with a flat surface. So that gives you an idea of how you can, Bert and Ernie, all they did was to measure actual values on the surface. They didn't use any extrinsic information at all. But those actual measured values compared with the predicted calculated values, the deviation between them gives them a measure of the intrinsic curvature of the surface. All right, well, let's look at another example. This time we'll start with a triangle. And of course, some things we know about the triangle. First of all, we expect the angles to add up to 180 degrees. So let's see if that works. It does. So we can change the shape of the triangle a little bit. But even though the individual angles change, the total is still equal to 180. Also, we know that there's a thing called the law of cosines that'll help us calculate the length of the side as a function of the other sides. So let's see what that looks like. What I've got here is I've got the values of the lengths of the sides as they're actually measured in the diagram. And you see A, B, and C over here listed. These are the actual measured lengths. And then these values are values calculated using the law of cosines. For example, this side squared plus this side squared minus twice their product times the cosine of this angle will give you the square of this side. So that's the formula that's used to derive each of these expressions over here. And the way it looks right now, everything is working just fine. Well, this is exactly what we'd expect. The actual lengths are the same as the value given by the law of cosines. But of course, I expect you see where we're going here. We've actually drilled down in our manifold to a very small neighborhood. And this is an example of the property of a manifold, that when we're in a very small neighborhood, everything looks like a plane. It's a flat space when we drill down far enough. All right, well, let's drill back a little and zoom out. I'm not changing the triangle here, but I'm zooming out to a perspective that's further away from the diagram. So now let me change the triangle and actually make it larger. And as we begin to do that, we're going to see some changes. First thing you'll notice here is that the sum of the angles is no longer 180 degrees. So each of these three angles added together gives 180.2, and you begin to see that there's a slight difference in the actual lengths and the lengths measured, calculated by the law of cosines. So again, that's because we're dealing in a curved manifold. And if we go back far enough, let me expand this out so we see the effect continue as we make this triangle larger. And eventually we'll get back to the point where we say that we're actually on a sphere. So these sides of this triangle are actually curved lines. They're straight from the perspective of the beings that operate on the surface, but they're curved because the surface is curved. And because we're dealing in a curved surface, then these values do not equate to one another as we'd expect. So as before, as we move back out away from a local neighborhood, we see this deviation, and that's a clear indication to us that we're operating on a curved manifold. Now, just to be sure, I mean, we're talking about lines that are straight here in the sense that when we go from this point to this point, we're not turning to the right or left, but the curvature, the line has to be curved because it has to follow the surface of the sphere. But the entire component of the curvature exists perpendicular to the line and the curve of the space itself. So if we look at each one of these lines dead on, you'll see that they are straight like this. Now lines that have this property that are straight within the manifold are known as geodesics. We go from one point to the other without turning right or left. So even though we've constructed this triangle with three geodesics, the sum of the angles is greater than 180, and the actual lengths here are less than what we would get if we calculated using the law of cosines. Now if we had a negative curvature, if we had something like a saddle manifold, then just the reverse would be true. These the angles would add up to less than 180, and these values would be less than the actual right here. It's only in a flat plane where these lengths will always equal the value calculated here, and the angles will add up to 180 degrees. Okay, one final example then. This time we have Bert and Ernie again on our manifold, and they're separated by this straight line. Only this time we're going to ask the two guys to see if they can walk parallel paths. We're going to have Bert over here begin to move forward at right angles to the line of separation like this, and we're going to have Ernie do the same thing. He's going to march forward again at right angles to this line of separation. Well, you know in a flat space that they're walking parallel paths. They'll never intersect. But you'll see in a moment that that just doesn't work out that way on a curved manifold. So let's zoom back out and watch this happen as these two guys try to walk parallel paths on this curved surface. Well, we're going to have Bert over here march in this direction. Now he's marching in a straight line. This is a geodesic path. To him it's straight. He's not turning right or left. He's going straight ahead, being very careful not to venture in either direction. And then we've got Ernie over here. He's doing the same thing. And again, they start out at right angles to this line. So they're doing the best they can to walk in parallel paths. But in spite of their best efforts, you see that their paths cross when they get up here to this point. Now, you and I know what's going on because these lines are actually curved. They're curved with the surface. And since this line down here is slightly curved, then these two lines pinch together as they get up to the top. But for people or these flatland creatures who live on this surface, it's a mystery to them. They get out here and they start walking at right angles to a straight line, and they come together. Well, you might recall, if you think way back to the days of Euclidean geometry, when you studied that probably in high school, you remember there was a postulate there. Euclid's fifth postulate said that given a line and a point not on the line, there's one and only one line that can go through the point that's parallel to the given line. Well, it turns out that's a very special case. That is only true for flat spaces. If the space is a curved space, such as this one where we have a positive curvature, then it's actually impossible to draw a line through this point right here that's parallel to this line. It's just not possible. It's not possible in any space that has a positive curvature. On the other hand, if we had a negative curvature, we had a line here and a point there, there are actually multiple solutions. We could draw many lines over here that will not intersect this one. It's only in a flat space where there is a unique solution to that problem, where we have a line, a point not on the line that is parallel, a line drawn through here being parallel to that. There's only one solution with a flat manifold. Now, it's that postulate, that given as this fifth postulate that leads to all of the proofs that you did in plane geometry. It's as a result of that that we're able to derive things like the fact that a triangle has 180 degrees. The derivation of the Pythagorean theorem is based on that. The law of cosines, all of those things are predicated on this principle that there's a unique solution through this point that's parallel to this one. Well, that's not true for anything except a flat space, and therefore all of those proofs that you did for plane geometry simply don't work in a curved surface. Hopefully these examples have given you some insight into the kind of information that's available at the intrinsic level. Now we're going to spend the next several videos exploring this topic in much greater detail. And we'll begin that process in the next video where we introduce the Riemann-Christoffel tensor.